An open box is to be made from a rectangular material of dimensions 8 inches by 6 inches by cutting a square of side x out of each corner and turning up the sides. Determine the value of x that results in a box of the maximum volume. So the way this is going to work, we have initially the distance from here to here. This is labeled as b. That is the distance 6 inches all the way across. What I'm going to do is cut out this region and this region from the sides. Well, actually, let me just go ahead and say I'm going to cut out all of these corners here. So what that's going to do is allow me to take what's left of the box, fold this upward along the line that I'm showing here, and that's going to create this box. It's going to be an open face box, so try and draw it in 3D here, although I'll probably not do it well. So distance along here, okay, and it'll look something like that. All right, because this is, the top is open, all right, but there is a base to the box. Now, the thing is, it's very tempting to say that the dimensions of this box would be 6 inches and 8 inches because that's what's given in the problem. However, when you cut these corners out, you're cutting away a part of the 6 inches away. So whatever you make the distance x from here to here, you're going to cut that out. So that's going to be 6 minus x, but then you're going to do it over here as well. So it's actually 6 minus 2x. So the distance this way of our box is 6 minus 2x inches. Similarly, the distance the other direction is 8 minus 2x. And then you can assume the height here to be x, because when we fold that up, that height value is x. Which allows me to come up with a function for the volume of the box, because that's what we want to maximize in the end, is the volume. So we need a function for volume. Since this is a rectangle, the volume is length times width times height. And it doesn't matter that the box is open. That would affect the surface area, but not the actual volume of the box. So what we can say now is the volume of the box is a length of 6 minus 2x times a width of 8 minus 2x times a height of x. So that right there is the answer to the first part. So you can go ahead and fill that in, and you're all done there. Now, the next part says to find the domain of the function v. So the domain here is going to be a feasible domain, because we can't have negative dimensions when we're dealing with a physical box. So you can't set the value of x to anything less than 0. So x has to be a minimum of 0. But there's also a maximum distance. If you set x to, say, 3 inches, then what's going to happen is your fold line is going to be like right along here. And when you fold that up, it's not really going to be a box anymore. So you can't have anything larger than 3 inches. So 0 to 3 is our feasible domain. You can also get that if you take the factors here and set these factors equal to 0 and solve. Oops. So you find x equals 3, x equals 4, and x equals 0. So basically, you can't go beyond 3, because that's a boundary. So 4 is bigger than 3, so you have to throw it out. And then x equals 0 is the lower bound. So that would be another way of thinking about it. All right, expand the function for easier differentiation. So to find the derivative of this function, as written, we'd have to use the product rule twice, and that would not be much fun. So expanding this would make it a little bit easier to find the derivative. So Let's try. 6 times 8 is 48. 6 times negative 2 is negative 12x. 8 times negative 2 is negative 16x. 2 times 2, that's going to be plus 4x squared. Then all of this is still multiplied by x. So I'm going to just go ahead and write in 4x cubed. 12 and 16, those would add together to 28. So minus 28x squared. And finally plus 48x. Now, that right there is the answer to part 3. I'm not going to copy it back over, but that's the answer to part 3. Next up, let's see here. Find the derivative. Okay, we've got it in a form to more easily find the derivative. Let's go ahead and do it. 12x squared minus 56x and plus 48. Okay, there's your derivative, so that's the answer to part 4. So they're really just walking you through the steps of this process. And there's not really a bunch of questions here. It's just walking you through the stages of the same question. Find the critical points in the domain of V. Now, to find the critical points, we would set our derivative to 0 and solve. I can see here, I think all of these are divisible by 4, so I'm going to factor out a 4. That would leave me 3x squared. 56 over 4, I think is 14. Yeah. So minus 14x. And then 48, I think that's going to give me 12. Let me just double check so I don't end up having to re-record a video. So 12 there, great. And this polynomial doesn't appear to me like one that would factor. So I'm just going to jump in and use the quadratic formula. So x equals negative b, so 14, plus or minus the square root of b squared. I don't know my 14s. Let's see, 196, all right. Minus 4ac, so minus 4 times 12 times 3, so minus 144, all over 2a, so all over 6. And let's see, so 14 plus or minus, so 196 minus 144 is 52. So square root of 52 all over 6. And let's see, I'm going to approximate that. So 14 plus the square root of 52 over 6. That's 3.535. So approximately 3.535. And then I have another root if I subtract, so 14 minus the square root of 52 all over 6. Oh, what did I do wrong? Oh, I didn't hit the 6 apparently. All right, 1.131. It doesn't tell me how many decimal values to use in my approximation. You can honestly, for the critical points, you could type in 14 plus the square root of 52. Well, of course you would write SQRT 52. But anyway, you could put that in like that, and the computer will always accept that as an answer. That's fine. You could also generally use 3 decimals. If it doesn't say, and 3 decimals is usually plenty. I think that's the default for the system, is 3 decimals. Okay, so, oh, yes. So I have put 1.131 in here, but I didn't put 3.535. The reason is my feasible domain tells me that this would result in a negative number for a volume. So that's not a critical number that I'm interested in. So 1.131 I am. The value of v at the left end point, the next couple of questions just have me evaluating the function at a bunch of different points, so let me just put the function n for y, and I'm going to use a table. 6 minus 2x times 8 minus 2x times x. All right, let me go into a table here. All right, so it says to evaluate v at the left endpoint and the right endpoint. They're talking about the left and right endpoints of the feasible domain. We know they're going to be 0 because that's how we came about with this problem. So 8 is the next important one, the maximum volume at associated with the critical value. We plug in the 1.131, and that gives me that value. All right, now if you're concerned about rounding issues, you can just type in 14 minus the square root of 52 all over 6, and that puts the, I don't want to say the exact approximation, the best approximation the calculator can do using 9 decimal places, so that you might get a little bit more accurate of an answer here. But in this case, it looks like it's pretty accurate, to 24.258. All right, and answer the original question. The value of the the value of x that maximizes the volume is 1.131.